join my voice to those of the speakers who have preceded me in thanking the organizers for this very interesting and, for me, educationally profitable meeting. And I feel a little bit embarrassed in addressing an audience which is certainly much more keen on this new type of phases that have been recently, I would say, characterized and discovered. So I will simply apply to their mercy just to be on the safe side. And most of the people I will cite in my work are who have been active in the field and have made important contributions to the field are sitting in this audience. So again, please forgive me for all the mistakes I will certainly put into my lecture, and all the misrepresentations of your work. This is another mathematical question, so I will try to be a little bit pedagogical and try to explain what is in these phases, what is new in these phases, and what is really fascinating in these phases. And then I'll try to suggest a couple of avenues which I have personally started to explore, but I'm just at the beginning. Everybody, I think, is at the beginning at this stage, and the construction of the mathematical theory of these phases. And so, I hope there will be some discussion, and of course, disagreement is welcome. Twist band nematics have been recently, I would say, rediscovered. Those signs of their presence had been scattered in the literature for quite some time. Essentially, what happens is it is a new transition, nematic to nematic transition, that some materials experience. And essentially, when you decrease the temperature in thermotropic liquid crystals, going from isotropic to nematic, there is yet another transition that follows, and it is a nematic to nematic transition. These were, early experimental studies. At that time, something was known happening at that secondary transition, but people didn't know what was going on, and so they simply said that there was a new phase that they simply called the NX phase. Now this phase has been named, and it is a twist band nematic. It has been recognized actually as a phase that had been previously predicted in two separate works, one by Bob Meyer and the other by Ivan de Zoff. All right, what is the key feature that the molecules that constitute the materials that undergo this transition have in common? Well, they seem to be bent and flexible. These are the two key issues that these molecules seem to exhibit. And rigidity, this is something which I think was believed up to a few weeks or a few months ago, that rigidity was a property that characterized molecules that would undergo only the transition from nematic to smetics, and that you need some kind of flexibility in these V-shaped molecules in these bent molecules in order to get to the new phase. But as I said, there are exceptions, and at the dining table last night I was informed that there are even more exceptions. People now know that there are materials for which not only you witness the transition from nematics to twist band nematics, but also from these to smetics. So of course, correct me if I'm wrong. So it seems that there is a large variety of circumstances in which this new phase arises, and it is not so clear that the characteristic of the fingerprint, the characteristic property of the molecules that constitute these materials is being flexible. Certainly, they need to be bent. So this is a kind of flexible or rigid. It seems to be that the key feature is the shape of the molecule, which is not chiral, by the way. It is just a bent molecule. It is a non-chiral molecule, but as we'll see in a moment, it gives rise to a nanoscale chirality. All right, the phase has been characterized by different groups. I'll show you some interesting and, for me, enlightening pictures that have been obtained by different groups. This was the European groups. These are all European groups, but of course, major contributions have been made in the LCI and in different groups in this country. So I'll simply stick to this prototypical material, which is CB7CB, and this is essentially the shape of the molecule. It is constituted by 3 parts, each of which is 1 nanometer long on average, and it is highly flexible in the between. So you could imagine these 2 arms to be rather rigid, and the spacer in between, which makes the dimer very, very flexible. Now, these are the transition temperatures that for this material have been characterized. The nematic isotropic transition is at 111 Celsius, and this is a first order transition which has a very small transitional entropy, and this is actually a property which is showed also by the secondary transition. Both transitions are weakly first order, and they are associated with a rather small entropic change. So these are also another property of this material is that on heating the crystal forms, the crystal melts forms at 102 degrees. So there is an extensive supercooling behavior in these materials. All these are elements of the characterization that I have alluded at a moment ago. All right, there is this very old paper, which actually was pointed out to me by Oleg, by Meyer, where essentially this phase was predicted on the basis of a very simple but effective electrostatic model. The idea was to associate a dipole moment to the bent molecule, which was, of course, directed along the symmetry axis, and a little bit of computation shows you that there is a chance for these bent molecules to be arranged if you allow for the interaction of the dipoles to be arranged in a twist bend fashion. What do I mean by twist bend fashion? I just borrow this picture from Dozov's paper, who essentially arrived apparently independently to the same prediction but based on steric interactions between these bent molecules. It is precisely the picture that has been repeated over and over again in these last few years. Essentially, you imagine that the molecule, the long axis of the molecule, which is now the axis joining the 2 tips of the bent molecule, in the ground state describes this conical arrangement. So the axis of the molecule makes a fixed angle with this precession axis, which is essentially the pitch axis in Randy's talk. And the difference, of course, here is that the angle that the molecular long axis makes with the pitch axis is fixed, and it is characteristic of the phase. And so this is the reason why such an arrangement is also called heliconical, because it is a precession that takes place along an axis, but the angle that the long axis of the molecule itself makes with the precession axis is fixed, and it is different from either 0 and pi over 2. In the limit, as this angle goes to pi over 2, then you recover the picture that has been so effectively represented by Randy in his lecture. So you recover cholesterics. Once again, it should be pointed out at this stage that these are not density waves. These are not preferred positions. There are no preferred positions for the centers of mass of these molecules. So really the centers of mass of these molecules wander around completely freely, but as soon as one of these molecules happen to be in a position, then the probability that it is oriented in this fashion is the largest. So these are not arrangements in space, but they are arrangements in the orientational manifold, in the orientational space. This is very important. These are not symmetrics. These are not symmetric C, because there are no density waves in this case. All right, this is the aliconical configuration that I just described in words, and there is this very nice and very impressive and convincing Monte Carlo simulation done by Memme in 2002, where he simply considered a bow-shaped molecule with the two arms interacting via Gay-Berg potential, and again in this simulation, there is no dipole moment, the one that Meyer had imagined in order to propose such a molecular arrangement. So in this case, it is not steric, the interaction between the two molecules either. It is just the classical Gay-Berg interaction, but between the two arms of both molecules, and in this case, the shape is fixed. No flexibility has been allowed in this computation. All right, so let us do some mathematics into it, and let us describe precisely what happens to this, to the ground state of the molecular arrangement. I call by M the long axis of the molecule. It is essentially directed along the vector that joins the two tips of the molecule, and this is more or less what I have in mind. This would be my bow-shaped molecule. This would be the direction of the polar vector. It is not a dipole. It is not an electric dipole. It is just the axis that symmetry allows here, because these two arms are symmetrically disposed relative to this axis, and this is a kind of polar vector that describes the symmetry of the molecule, and this is the, so to say, director director that describes the symmetry, because of course if you change m into minus m, nothing changes, because again the molecule is neither chiral nor polar. And the idea is that the molecular arrangement in the ground state would be this one, and this would be the clear representation of one of the two variants. So if you take here plus or minus sign, you get the two variants. This is the right-handed thing, and the other one that you get by changing plus into minus would be the left-handed. There is one way of measuring the chirality of such an arrangement, which is simply borrowed from hydrodynamics, and it is the Olicity. This is a notion has been introduced long ago by hydrodynamicists. In that case, of course, the m field would be the velocity field, and if you apply this notion to the m vector field, m director field more properly, this is what you get, and you get a minus plus here for so a negative, a minus sign here. So a negative Olicity for the right-handed arrangement. Unfortunately, this dichotomy, the positively oriented helix has negative Olicity. So this is the reason why, well, this is definition is a little bit uneasy, because it changes the sign. And 2 pi over q is the pitch of this arrangement. So this is what is presumably happening at the microscopic level. This is presumably the way molecules want to be arranged in their ground state. And here there is, well, very, I would say, rather impressive experimental evidence of such an arrangement, which has been able to measure the pitch of this heliconical molecular arrangement, which is in the range of tens of nanometers. And so this is the reason why these materials are completely different from cholesterics. The pitch that cholesterics exhibit is in the range of micrometers, while here this, the pitch exhibited by the heliconical arrangement in twist band nematics is in the range of tens of nanometers. And this conical angle, which we'll see in a moment, depends also on temperature, is in the range of tens of degrees. And I think that this is one picture coming from Oleg's lab, and this is the free from Boulder. I'm sorry. I tried to be equidistant but between the two groups, but presumably I failed. Never mind. So anyway, there are two pieces of important work, and I will not, of course, stand here and take sides. All right, this is a very nice, this is one nice way of illustrating these pseudo layers. I like this very much. I read it in one of Oleg's paper, and he was very keen in introducing this name, pseudo layers instead of layers, because these are not really layers. These are not mass layers. These are pseudo layers in the sense that they are simply recurrent layers for the orientation, and they are not recurrent layers for the positions of the molecules. And of course, here everything seems frozen, because indeed this is the freeze-fracture transmission electron picture. And you see here, these would be the layers, and the pitch would be, of course, orthogonal to the layers. And there are several evidences pointing to this direction. This is another paper which was published again from another, this is a European group, and they have actually documented the way that cone angle depends on temperature. You see from here, it starts from almost zero at the nematic twist band nematic transition, and it goes up to 30, 40 degrees. All right, and again, this is another picture taken from Oleg's lab, and here you see this pseudo-layer undulation. It is this is an explosion of this tiny area here, and you can see this would be the orientation of the layers. And once again, you see that these tiny rods here would represent the twist axis, what Randy called the pitch axis, and what I call the twist axis, but they are just the same thing. Would be. All right, theories. What do we know about theories? All right, the idea is that if you try to do a kind of macroscopic model starting from this microscopic arrangement, you immediately realize that the polar vector P would simply average out to zero, and so there is no reason to suspect that these phases are indeed polar. And you might introduce at a macroscopic level a new director, which is now to be intended as the average of the M director. All right, de Zoff has an elastic theory based on this kind of premises, and the theory he has is based on the assumption that the band elastic constant of Frank-Rosen energy is negative, and this, of course, is counteracted by some quartic terms and some other terms which are quadratic in the second gradient of n. This is a very complicated theory. It is very demanding because it is a second gradient theory. It is very demanding because if you just count the number of invariants that you can construct in terms of these measures, then the number gets up incredibly rapidly, and you get plenty of elastic terms allowed in the theory. There has been another proposal made by Jonathan and his students based on the idea that there is a kind of local flexoelectric interaction between these bow-shaped molecules, and this is a quadratic theory in the gradient of n, but which has a positive band elastic constant, but the coupling with the flexoelectric energy introduces an effective negative K3. This is quite interesting. It simply introduces this kind of polarity at a local scale, and it is completely compatible with the absence of polarity in a greater scale. All right, there is also recently appeared an attempt to express these phases in terms and represent them in terms of an extended Myers output theory. So the strategy I would like to present is based on the idea of presenting a detailed analysis of what I call the vacuum manifold. The vacuum manifold is essentially constituted by all gradient fields, gradient n fields, which would pertain to this heliconical arrangement. So the idea is, suppose just pick up one of the two possible ground states, pick up only one of the two helicities, and compute the gradient on such a fundamental ground state. If you compute the gradient, then you realize that you can always express it in this form, with EZ being the twist vector, the vector along which the helix is winding about. And then what you simply introduce is this measure of the natural distortion, which we call the twist tensor. So imagine that you know n, and imagine that you know the twist vector t. Then this tensor here, which I call the twist tensor, would represent the ideal gradient of n that would correspond locally to the heliconical arrangement. Of course, as Randy said, for example, for a moment ago, there is no guarantee in cholesterics that this is the real arrangement. But if it is, then the energy is minimized. So the idea is that what you need to do is just to compute the elastic energy which is needed to produce a distortion starting from any of the representatives of the ground state. But the ground state now is rather rich. It is it is represented in this way. So it is, if the gradient of n is equal to one of these twist tensors, then you say that you are in the potential well and you pay nothing, because this is a natural distortion. It is a distortion that the directed field would like to have if it were left to itself. And so this is precisely what is a vacuum manifold. The energy you need to construct must vanish on this manifold, because this manifold, any member of this manifold, actually we'll see in a moment that it is a three-dimensional orbit. It is a three-dimensional manifold. And such, any member of this three-dimensional manifold is a distortion that would correspond to a locally twisted configuration, which costs nothing. And so this is the idea. Again, it is easy to see that such a manifold is homeomorphic to this Cartesian product of this two sphere with a one sphere, so it is a three-dimensional. And so this is the idea. The idea is that you count the energy which is needed to go away from the potential well. So what you need to do is just to count the energy that it is necessary to go away from the vacuum manifold. And the idea is that this is a tensor, a fourth rank tensor, which depends only on the local arrangement, and T is any vector that makes the conical angle which is prescribed by the experiment. So the idea is you can also give a kind of metric interpretation. You ask yourself which is the energy per unit volume, which is the energy density associated with the given distortion grad n. Well, it is given by the distance in this metric between the actual distortion in a point in space with the closest member of this vacuum manifold. And the vacuum manifold is parameterized, of course, by T, which is the twist axis. So, of course, now the T axis is a member of this twist manifold, of the vacuum manifold, and so what you get is a minimum principle in which you need to minimize in both fields. In the field T, which would represent the optimal orientation of the twist vector and the point, and the local distortion in grad n. So if you just do all the algebra right, this is precisely what you get. This is the most general quadratic expression in the grad n's that has this property. Of course, here and these are the Erikson's inequalities appropriate to this theory, which guarantee that this is really definitely positive, that we are really measuring distortions away from the vacuum manifold. And so this is the explicit formula, but you should really be reminded that here not only n, also t is an unknown, because it simply singles out the twist tensor in the vacuum manifold, which represents the closest member. All right, just a few closing remarks. As I said, this theory is different from the classical theory of pneumatics because it features two directors, T and N. The second remark is that physically T represents the optic axis is the one that we can really see, because this modulation is so tiny that we don't see it optically. So the only thing that we can hope to see is just the normal to these pseudo layers, and the normal to these pseudo layers is precisely given by this unit vector T. Of course, properly, as it should be, this energy density is invariant under inversion of either n or t, showing that both vectors actually are directors. And finally, if you take the limit as either q goes to 0 or t goes to infinity, you simply recover in this theory the classical Frank-Ozen energy for classical pneumatics. And if you take theta to be pi over 2, then actually you recover an alternative form for the cholesteric energy. And just an aside is that in such a form of energy, you need not require K24 to be 0, which was the requirement needed in the classical theory in order to guarantee positive definiteness of the energy. In this case, K24 stays positive. I think that I can just pause here. What this can be, of course, it was prepared for a much longer lecture, but I simply want just to make one remark in case people are interested, that in a theory like this, what you need to care about is the possibility of merging together the two helical variants, and this actually can be done by proving that there is an interface between the two differently oriented, the two different helicity domains. Such an interface has been completely characterized in geometric terms as a specific developable surface. But my time is over, and I would be happy to answer specific questions on this and other points.
We have time for questions.
You showed simulations. What was the potential like in the simulation?
It was a Weber potential between the two rigid arms.
And some constraint about the flexible?
No, there was no flexibility allowed.
I see.
These were rigid V-shaped
Oh, I see.
molecules.
Right.
Good job.
So, with the theory that you're presenting here, I couldn't quite follow. Does it make different predictions from what I worked on or what Dozov did, or is it, a different way of presenting the same physical concept?
Well, it is a different theory because first of all it has two different descriptors. In your case, you had the polarization P and you had the nematic director, and they were coupled. In my case, I have the nematic director and this twist director. So, and when you minimize the free energy functional, which of course is obtained by integrating this density, then you need to care about the two fields. Now, one point is that the n field here contributes to the energy via its gradients, while the T field doesn't contribute to the energy via its gradient. So it is what is sometimes called a zero-term element in the theory. And so, but it comes into play via the constraint, because the constraint between T and N says that the angle between T and N must be constant. So you simply need to minimize among all possible fields N and T, which make this angle the conical angle. And of course, for example, you can redo Frederick's transition in this fashion, and you get a different dependence of the threshold on the thickness. Actually, you get a dependence on the thickness in this case. So it is a different physics. Anyway, different predictions. I don't know whether it predicts the correct physics. But it is based on the idea, essentially you recover the classical Franck's energy by simply saying, all right, which is the indistorted case in Franck's energy. The distorted case is a uniform alignment, but in whatever direction. Even in that case, there is a vacuum manifold, and the vacuum manifold does not contain a single element. It contains S2, essentially. It is a rich manifold. In this case, it's a bit more complicated because you get N and T, and they are related. And so actually, the vacuum manifold is a three-dimensional orbits of cones. Topologically. And what you do in the classical theory, you measure distortions away from the uniform field, whatever oriented. In this case, you measure distortions from any member of this manifold. So it is just the same idea. The only difference is that the manifold, the vacuum manifold, is different.
Can you show the expression for your Franck-Zinn version of Yes. So, so if we consider that N has a very fast rotation around T vector, and that's exactly what happens in NTB phase. So in this case, probably we can consider this expression as an elastic energy for macroscopic elastic energy for NTB phase if we will go from actually the gradients of your local director to the gradients of a T vector, which is some kind of average director in NTB phase. Am I correct or not?
Well, I think you are correct. The point is the interpretation of this energy is, and of the director N itself, is not that clear. This is a macroscopic, this is really a phenomenological theory. And, but you are assuming that you can...
It's some kind of, if you make coarse grain
Right.
approximation and say, forget about everything else, we have very fast rotation. Then when we have some kind of gradient of N, we can go we make averaging over the pitch, and then we will have gradients of T, which appeared as a result of constraint, what you're talking about, that gradient N and T should
If you perform the average, this is a possible way. If you perform the average by taking into account the constraint, then you might be able to transform these gradients into the gradients of T.
Time for one more question.
Two questions.
I said what?
Combine them.
Semicolon. Well, so, back in '96 or something, Adrian Parsigian and Helmut Strey, they were going around, they had DNA. And they had DNA and they thought it made a hexatic phase. Right? So they had DNA and they did X-ray scattering and they had looked like they had hexatic order. So some of us analyzed that and said, well, if it had hexatic order, the hexatic order would have to twist. So there was a second director, which was the direction of the hexatic order. There's sixth director and then the manic director. And so it's not dissimilar from this, although it doesn't mean that the actual twist bend state has hexatic order. There's just some other vector. It has to be there just from the geometry to support this twist bend phase. My question is, which cues there have to be the same, which cues can be different? See, you have Q 3 places.
It's the same cue.
Why? Why is it the same cue?
Because the cue comes from the vacuum manifold.
But why is it the same cue? Why do you know that one director wants to rotate around at the same rate as another director?
No, this is the only end that rotates about t.
This is N rotating around T.
Right.
But
And t is slowly varying in space.
I think you could have a different cue. I think the second cue with the K24 could be a different value.
Yeah, I'm going to recommend that you do. Let's thank our speaker one more time.